Hello everyone, I'm Julian and I'm a Developer Specialist SA at Amazon Web Services. I'm part of a team called DevAxe, which is short for Developer Acceleration. I work with developers on AWS to help them understand how to apply the right patterns and practices to build highly scalable, available, and secure systems on AWS. Today, we'll be covering how to automate your application delivery across Mac, Windows, and Linux at scale and on demand. In this talk, I'll cover what a deployment process looks like for an on-premise build server. This is the first architecture that I used when building out my application. Then I'll go into the requirements of what we would want in a pipeline if we were to leverage cloud services to run the build pipelines. I'll then cover how customers can build pipelines on AWS using some of the code tool services. And finally, we'll look at how we can deploy custom pipelines, and this will be the main focus of today's talk. Now, before we get started, I do want to mention that today's talk is a level 300 talk. So I'm going to assume that you already know the benefits of having a CI/CD pipeline. I'm also not going to cover the basic AWS services, and I do expect at least a solution architect associate level of knowledge. In this talk, I won't be covering any branching strategies, but focusing on the actual pipeline flow and cover some of the finer details that caught me out when I built this pipeline. Now, I first want to set the overall CI/CD pipeline flow that we're going to be using for all the pipelines in today's presentation. This is the typical flow that we see our customers use when building pipelines. We start with a developer or development team programming an application on their local machine. And for me, this was my MacBook Pro, and I was a development team of one. For your business, this could be an application development team or any other team developing applications. You would create the application code, set up any configuration the application might need, and write and run unit tests to get some really quick feedback on the quality of the app. Once the tests pass and our application is ready for release, we would push these changes into a feature branch and merge it into mainline. A push in a code repository would trigger the pipeline to start and run the first pipeline step, which was the build phase. This would build the application using any production variables, certificates, or endpoints that we need. The build server will then be notified of this change, clone the repo, install any dependencies that might be needed, and start to compile the application. That is, if it is a compiled language. Once a build artifact has been created, this will then trigger acceptance tests, and these could consist of performance tests, integration tests, UI tests if the application has a user interface, and regression tests. Once the application passes and has been approved, it's ready to be released. Now, this is the step that usually differs quite a bit depending on what it is that you're trying to build. If it's a web application, we would deploy to the web server. If it's a mobile application, we would deploy to the App Store. Now, this is all quite a process to build and get it set up, but once it's running, it would save time and guarantee a certain level of quality. Now, before the cloud, if you wanted to have a CI/CD pipeline, our customers would need to purchase and maintain a build machine, and this will be responsible for the whole build process. The development team would push new features into a repo like GitHub or Code Commit, and then this will trigger the on-premises build machine to build and release the application. This build machine will be responsible for all the pipeline steps, which would lead to some pain points. Each build machine would have to have the whole pipeline set up, and all the resources and libraries would need to be on this machine. If you needed to build for a different machine architecture, you would have to go out and buy a new machine. You would also have to log into each of these machines and to make sure that the pipeline is up to date as well as the machine. You'd also have to log into them to check the build process, track the process of any other builds, and get log information if something went wrong. This build server also became a single point of failure. If your network connection was interrupted or the power went out, you wouldn't be able to release any builds until the problem was resolved. The build server you purchase is also a capital expense on the business, and the resources on the machine, like storage, compute, or memory, are finite, And once you hit any of these limits, you would need to go out and get another physical machine. And finally, it would always have to be on, and you would be paying for the machine running costs, even when there aren't any active builds. But what if we didn't have these limitations? If we take these limitations into consideration, and we rebuild our pipeline, there are certain requirements that we saw our customers asking for time and time again. The first is to be able to scale to satisfy demands of our build process. If we need more memory, we should be able to click a button and add it to our build machine. We'd also want to integrate with the services and platforms that we're already familiar with. If the application lives on AWS, why can't our build pipeline exist there too? At AWS, security is job zero, and we would expect to have security at every level of our pipeline as well. And finally, we don't want to be limited by the physical hardware on the machine. At AWS, we currently have native support for Windows or Linux-based desktop applications or web applications. Now, the overall process flow would look something like this. Code will be checked into a source repository like code commit, and then this will trigger our code pipeline to start the build pipeline. Code build will then receive the latest commit and start building our application. After code build finishes building out our app, it can then run acceptance tests on the built artifact. And finally, once all our tests pass, we can deploy our web app or service using code deploy. If we were to look at building mobile apps for Android, the pipeline would change slightly. After code build runs tests on the built application, we can add an extra layer of certainty to see how the app behaves on real devices. Device Farm allows us to take an Android, iOS, or web application and run concurrent tests on real physical devices. We can then verify the application works and displays as expected before we release the application to the App Store. For the deployment, we can use Code Build to push our app to the Google Play Store. Now, this is great for Android apps, but what about iOS or Mac applications? We saw our customers building Apple applications through one of three ways. The first way is by purchasing a fleet of Mac servers and running them in the office or data center. Now, these environments required capital expenditure and typically have a 3 to 5 year depreciation schedule that limits the ability to upgrade and take advantage of the latest innovations. There's also a physical and operational overhead associated with managing the hardware. And finally, the build server became a single point of failure if your network was interrupted or if the power went out. Alternatively, customers might have been using a Mac as a service provider who offers rental of Apple hardware. You would have to pay a monthly or annual contract to keep the machine, and the scaling notice period would require days to months notice just to scale your capacity up or down. Then, once you had access to the machine, you would have to pay for the data transfer time and the cost. And last and most common option that customers opted for was to use a continuous integration service provider. This would mean that you don't have access to the underlying operating system. So if you needed a tool or customization as part of your build process, you were out of luck. These build services are also often running on multi-tenanted devices, and you would be sharing the underlying hardware with other customers of the build service, leading to potential security risks. However, on November 30th, AWS announced the general availability of EC2 Mac instances, making macOS available on AWS for the first time. These instances were built and designed for Apple developers to enable them to focus on code and not infrastructure management. To build, test, sign, and publish applications for Apple devices, you're required to use Xcode, which can only run on macOS. With the new macOS EC2 instances, developers can bring their current toolset that they're using for building apps into the cloud, and they also gain access to the broader AWS ecosystem. So how can we go about building a pipeline for a macOS system? The CI/CD flow is the same. We'd first push the code into code commit, and this will trigger code pipeline. Next, we need to incorporate a custom workflow step using AWS step functions and a custom build machine. Now this custom workflow step allows us to choose the build machine that we want to use in CodePipeline. CodePipeline will trigger this custom workflow step using the native step function invoke integration and kick off our state machine. So let's have a look into this workflow. A step function workflow is comprised of a series of steps. Our state machine has a single step called build. This step will allow us to run build commands on a target build machine. If you have other steps that are required in your custom workflow, then you can add them in this state machine as well. When defining steps in the state machine, you need to define what type of step you want to use. In this case, we're going to be using a Lambda invoke waitForTask token type. The reason is that this allows us to go off and invoke other tasks to take place while pausing this pipeline and waiting for those other tasks to complete. We could call the Lambda function directly from CodePipeline to perform actions, but Lambda functions have a 15-minute timeout and would be invoked synchronously, meaning we would be paying for the Lambda function execution while waiting for a result. If we're waiting for a result and the Lambda function times out, CodePipeline would re-invoke the same Lambda function with a continuation token, which you would then have to handle. Step functions allow us to perform multiple actions in parallel, and can also provide us with paths in case an error occurs, which can be handy if we need to run a command to clean up the build machine if needed. Now this step function workflow takes targets passed through from the CodePipeline step, which tells us which build machines to run commands on. We're also passing through the branch name, the repo name, and the repo URL from CodePipeline. Now these parameters will then be passed to a Lambda function in the event parameter of the Lambda handler function. This Lambda function has 4 responsibilities. The first is to get the build script that we want to run on our build machine. The second is to take the commands that we want to run on our build machine and wrap it in code that allows us to talk back to step functions in the event of a success or a failure. The third is to upload this new script into S3 for this particular job. And finally, it's responsible for sending a command to the build machine with the location of the new build script and kick off the build. Let's look at each of these steps in a little bit more detail. The Lambda function will reach to an S3 bucket containing the build scripts that are approved for running on build machines. It would need access to this bucket, and it would also need to know which script to run from the bucket, which we pass in as a parameter from the state machine. In this instance, we want the build script. For the next step, we need to look into the code of the Lambda function. Inside the Lambda function, we need to take the parameters passed in from step functions and the script that we want to run. We then wrap the build script in another bash script wrapper. This bash code makes sure that we can communicate back to step functions. So if all our commands that we ran were successful, it takes the task token and it calls the step function API with success. If not, then it will call step function workflow with a failure. Now, it's important to note that here I use bash, but you can use any programming language that you're comfortable with. The reason that I chose bash is because I knew that it would run on any Unix system without any extra prerequisites. So let's jump back into the workflow. The third step now is to upload this new script that we wrote back into S3. Finally, the Lambda function uses AWS System Manager run command to invoke the build script on our build machine. Let's look at run command in more detail. AWS Systems Manager, or SSM run command, lets you remotely and securely manage the configuration of your managed instances. Now, a managed instance is any EC2 instance or on-premises machine in your hybrid environment that's been configured for Systems Manager. EC2 instances come pre-installed with the AWS System Manager agent, so you don't need to install this agent yourself. Run command takes predefined or custom documents which contain different actions and then runs these documents on your target machines. In our custom pipeline, we'll be using run command document called AWS run shell script, which takes shell commands and runs them on your target machines. The great thing about using run command in this instance is that we don't need to know any Bastion hosts and we don't need any SSH keys. We can access the targets through IAM permissions. So let's hop back into the pipeline. Here we're going to use SSM run command to issue a single command to our build machine in a private VPC. For this to work, we need to enable port 443 in our EC2 security group and add a VPC endpoint to allow System Manager run command to see our build machine and issue commands. To protect the Lambda function from going rogue and having a malicious user running code on any machine, you can lock down which run command documents are allowed to be run and which targets they're allowed to be run on. All output from the command is sent to a run output bucket or a CloudWatch log group. Now the command that we run on our build machine will tell the build machine to pull out our wrapped build script from our script bucket. The run command document will then tell the build machine to execute the build script. At this point, run command will finish and return a success. It's a fire and forget operation in our build pipeline. The reason that we do this is because it allows us to run our build script as a different user than the user that run command uses. The build script will continue to execute, and as one of the build steps, it will publish a build artifact containing our application into an artifact bucket. Once the build script is finished, our step function wrapper code will run and communicate the S3 key and our latest artifact back to step functions, along with the success status. This will complete our custom step and finish the step function custom workflow. CodePipeline will detect the status change and continue our build pipeline. Now, so far, we've built out an artifact on the custom build machine. Next, we can actually test this latest build. To run tests in CodePipeline, we can reuse code build, and once those tests succeed, we can deploy our application using code deploy. So let's now look at an application of this custom pipeline step pattern. In my demo, we'll be covering how to build an iOS application using the latest EC2 Mac instances. In the demo, I'll go through creating a new commit, pushing to code commit, which will then trigger our pipeline. CodePipeline will then start our custom pipeline step using the pattern that we just discussed, and we'll use an EC2 Mac instance as our build machine. After the app has been built, we'll then pass our build to AWS Device Farm to test it out at any scale on real physical devices. In this demo, I'll be compiling an iOS application using a custom pipeline step in CodePipeline. This is the iOS app that I'll be building in this demo. It's running in a simulator, and we can see that it's nothing too special, but for our purposes it'll do. Now this is a public code repo, and I've just forked this code into a new repository hosted on AWS Code Commit, which we can see here in VS Code. Now I've also added the Appium test file, which we'll use to test the application. And I've also got a Fastlane file in this repo to help with the build script automation. Let's go check out our pipeline. So this is the pipeline that will build our demo application. It currently has 4 actions. The first is the source step, and this is triggered when we push a new commit to code commit. This step will take our commit, zip it up, and add it to an S3 bucket used as the artifact store for this pipeline. After that's complete, it'll trigger the build step. In our build step, we'll pass our parameters from the previous step to our AWS step function, which will execute the build on a custom build machine. When it completes, we should have a built artifact in another S3 bucket. I've had to add an extra step which takes the build artifact from that extra S3 bucket and adds it to our code pipeline artifact bucket. We need to do this because for our final step, we want to integrate with Device Farm and run our built app on real devices as part of our code pipeline. The integration with Device Farm needs our build app to be in the same code pipeline artifact bucket. Now, I'm not going to run through this code, but what it's basically doing is getting the S3 key and the bucket from the output of step functions. It's then copying that app from the build bucket into our code pipeline artifact bucket. Finally, we'll submit the job to Device Farm to test our new built application with our Appium tests in the source repo. Let's look at the step function workflow and see what it's doing. If we click on the Definitions tab, we should be able to see the state machine definition. And in this document, we can see here that we're running a single Lambda function, passing a task token in the payload, along with the parameters from CodePipeline. Now here I've separated the parameters into pipeline parameters and command parameters. The pipeline parameters I'll use in the Lambda function, and the command parameters I'm using in the build script on the build machine. It's here that I define what script I want to run on the build machine in the phase parameter. Let me show you what that script contains. So here's the build script that we'll use to build our application. It's cloning our repo with parameters passed in from the command params section in step functions. Now if we go into the issue command Lambda function, we can see what the Lambda function is doing and how it passes parameters to the script. Alright, so we've opened the code for the invoke Lambda function. We can see that I'm pulling out some parameters here. Then I'm pulling out the build script from S3. I'm converting the command parameters from JSON to bash variables. And finally, I'm wrapping our step function handler code around our build script. After we have a new script with all the parameters interpolated, we can upload it back to S3. The key will be the job ID, which is generated from CodePipeline. Once that's uploaded, we can then take the target values from step functions and issue a run command on the target machines. The command it will run can be seen here. The command will allow me to run the next section as a different user. Here I want to run the script as an EC2 user on the build machine. I'm copying the new S3 script to the build machine, changing its permissions so it can execute the script, and then I'm running the script. That will then cause this Lambda function to finish without any errors. So let's go back to VS Code. Now I'm just going to create a small commit here, and now that we've made it, we can push it to code commit. Now we can see our pipeline in action, so let's jump back into the console. Alright, so here we can see our pipeline being triggered by the commit, and it's here that it'll be copying the latest change into the pipeline artifact bucket. So now it's triggering the build phase. Right now we should be able to see the step function execution. If we click on the Input tab here, we can see what inputs were given to the step. And if we scroll down, we should be able to see the payload that the Lambda function received. If we now go to Run command, we can check that the command was run successfully. So we can see here that our command was successfully run. And if we expand it, we should be able to see the command that was run. Now we can go back into step functions and wait until the process completes. In the Output tab, we can see an S3 bucket containing the latest app build. And if we go back to our pipeline, we should see that the command is finished and that we're testing out our app in Device Farm. Let's go into the Device Farm console and see it running. So here in the Device Farm console, we can see that a new test is running. So I'm going to pause the video here and we're going to come back once it's complete. Alright, so all our tests have complete, which means that our app is ready for deployment. If we click on the Device Farm Run, then we click on one of our test devices, we should be able to see the video output of our tests. Alright, so now let's go back to CodePipeline, and we should see that our pipeline has also successfully complete. Awesome. We've now seen how we can use CodePipeline and a custom build step to build iOS applications. In the demo, we saw how we can achieve a custom pipeline step, like building on a private EC2 instance running macOS. We also tested our application using Device Farm. But we could take this a step further and use another custom pipeline step to release the application to the App Store. There are a lot of possibilities of what you can achieve when using this pattern. For example, you can build a native application across multiple platforms, all with shared configuration, and release them all at the same time. You would also use this to build and integrate any native libraries that you might need in your main application build. And with AWS integration, there are endless possibilities. For example, you can take this architecture and build a front-end dashboard that gives you insight into the detailed progress of your builds, and also collate all the logs into a single location. There are many more possibilities than what's listed here. So this is where I ask you all to go out and make the pipeline work for you. Have a play around with this pattern and see what you can achieve when you're not limited by the build process. Make the pipeline work for you. Now, if you're watching this talk, it means that you're here to learn. If you or your organization want to learn how to use AWS services at a deeper level, check out the AWS Training and Certification website. We offer a range of different training modalities to suit your personal and business learning styles. I'd like to personally thank you for giving me your time and watching this talk. If you have any questions about anything that I've covered in today's presentation, please feel free to reach out to me at jpittis@amazon.com. I'd love to hear how you're currently managing your CI/CD pipelines. And if needed, get in touch to see how myself or anyone in the DevAX team can help accelerate your developer's journey to the cloud. There'll be a brief survey after this talk. And if you've enjoyed this video, don't forget to give feedback. Thank you.